On this question, we want to find the critical numbers, find where the function is increasing or decreasing, find all relative extrema. From this function, f of x equals x squared minus 1 to the 2/3 power. When we're looking for critical numbers, we need to find where the derivative is equal to 0 or undefined. So since we need to have the derivative, let's calculate that first. So once again, our function is f of x equals x squared minus 1 to the 2/3 power. To calculate the derivative, I'll use the general power rule or a combination of the power and the chain rule. Depends on how you want to think about it. So the derivative will be 2/3 times x squared minus 1 to the negative 1/3 power. And we'll chain by taking the derivative of the inside, which is 2x. Now I'll rewrite this as 4x over 3 times x squared minus 1 to the 1/3 power. So I rewrote it this way. This has a negative exponent, so that's how I was able to write the 1/3 in the denominator. And then I multiplied the 2 times the 2x to get the 4x in the numerator. So this is the derivative, and to find the critical numbers, we need to find where this derivative is equal to 0 and also where the derivative is undefined. So to find where the derivative is equal to 0, we can take a shortcut, and instead of setting the entire derivative equal to 0, we can set the numerator equal to 0. And we'll divide both sides by 4, and we get a critical number of 0. Then when we're looking for where the derivative is undefined, this derivative is in fraction form, which we can't have 0 in the denominator, so we can find where it's undefined by setting the denominator equal to 0. And once again, I can take a shortcut by just setting this factor equal to 0. And I'll add 1 to both sides. X squared equals 1. If I square root both sides, I get x equals plus or minus 1. So I have critical numbers of -1, 0, and 1. And once I identify the critical numbers, I'm going to use those critical numbers to find the intervals where this function is increasing or decreasing. So I take the critical numbers and I use the critical numbers to divide up the number line into intervals. I want to make sure I write those critical numbers in order from smallest to largest, because the real number line is broken up, or sorry, is stated from smallest to largest, from left to right. So we've laid out the critical numbers on the number line. Remember, the critical numbers are our potential relative extrema. So we're going to be using those critical numbers later on to find the relative extrema. But those critical numbers divide up the real number line into these different intervals. So let's write down those intervals. We have this interval here, which goes from -infinity to -1. This interval, which goes from -1 to 0. This interval from 0 to 1, and this interval from 1 to infinity. And we want to know whether those intervals are increasing or decreasing for the original function, and the derivative is going to tell us that. We're going to choose test points in each one of these intervals. So I'll choose -2, -0.5, 0.5, and positive 2 as my test points. And I'm going to substitute those into the derivative to determine the sign of the derivative. If the derivative is positive, the function is increasing on that interval. If the derivative is negative, it's decreasing on that interval. So let's take our test points, and we're going to substitute them into the derivative. So our test points are negative 2.5, negative 0.5, 0.5, and 2. And let's use our calculator to help us make this go quicker. So in the y equals menu, I'm going to type the derivative for x over, my parentheses around the whole denominator, 3 times x squared minus 1. That's raised to the 1/3 power. And I'm going to close the parentheses for the denominator. And I'm going to use the table feature. I believe I'm in ask mode. So I'm in ask mode, so I'm going to select my test point values as the x values, negative 2, negative 0.5, 0.5, and 2. And we are taking note of the sign of the derivative, whether it is positive or negative, and that will tell us whether the function is increasing or decreasing on that interval. So we've got negative, positive, negative, positive. And so for our intervals, negative, positive, negative, positive. So this is going to tell me that the positive intervals are increasing. So on the interval from -1 to 0, and also on the interval from 1 to infinity, our function is increasing. And then on the interval from -infinity to -1, union with 0 to 1, the function is decreasing. So now that we found the intervals of increasing and decreasing, we can use the chart that we've built to also identify any relative extrema. We find relative extrema when we see a change from increasing to decreasing or decreasing to increasing. So looking at our first two intervals, we have decreasing and then increasing, and that is going to create a minimum. So at this critical number of -1, we're going to have a relative minimum. So the first relative extrema, which has the smallest x value, is going to be -1. I haven't found the y coordinate yet. And we know that it is going to be a relative min. Then if we continue on our number line, over the next critical number we have increasing to the left and decreasing to the right, which creates a maximum. So at that critical number of 0, we have a maximum. And then finally, over our last critical number, to the left is decreasing and to the right is increasing, which creates a minimum. So at that critical number of 1, we have a relative min. Now this is stating to write the relative extrema as an ordered pair, so I need to find the y coordinate. Now these extrema that we're finding are extrema of the original function, so the y coordinate of the ordered pair will come from the original function. So I'm going to make another chart, this time using those critical numbers where we found the extrema, -1, 0, and 1, and we're going to substitute those into the function f to find the y coordinates. I can use my calculator once again. I'm going to type into the y equals menu the original function. I can turn off the derivative. I'm going to turn on the original function. I guess it's not turning off and on. So we'll just remember that it's in y2. So we've got parentheses x squared minus 1 raised to the 2/3 power. I'll go back to my table and let's adjust these x values to be the ones that we were mentioning, -1, 0, and 1. And we have y coordinates of 0, 1, and 0. So now I'll be able to complete these ordered pairs. We have the ordered pair -1, 0 being a relative minimum, the ordered pair 0, 1 being a relative maximum, the ordered pair 1, 0 being a relative minimum. So we have applied that first derivative test, and that first derivative test is recognizing this change from increasing to decreasing and increasing to decreasing to locate those mins and max. But you needed to do the work to build the chart first in order to read the chart. So in this example, we are given f of x equal to 24 over x squared plus 12. And we're given the second derivative of f double prime, to be 144 x squared minus 4 over x squared plus 12 to the 3rd power. So that's nice. We don't have to do any derivative calculation on this problem because it was given to us. We're going to find the critical numbers of f for the second derivative, and we're going to find the intervals on which f is concave up or concave down. Concavity is something that we get from the second derivative, so it's nice that that was given to us here. And we want to find all points of inflection for the function. Points of inflection is also something that we get from the second derivative. So when we're looking for critical numbers for the second derivative, we want to find when the second derivative is either equal to 0 or the second derivative is undefined. So let me erase that. So I'm looking for critical numbers for the second derivative. So I'm finding where the second derivative is equal to 0 or undefined. So to find where the second derivative is equal to 0, I can take a shortcut and just set the numerator equal to 0. I can divide both sides by 144 and get x squared minus 4 equals 0. X squared equals 4. Square root both sides to get x equals plus or minus 2. So we get some critical numbers from the second derivative being equal to 0. And then I'll look for where the second derivative is undefined. And to find where the second derivative is undefined, you would set the denominator equal to 0. Once again, I'm taking a shortcut by only setting what's inside the parentheses equal to 0. And when I subtract 12 on both sides, I get x squared equals negative 12. And if I square root both sides, I get imaginary numbers, plus and minus I square root of 12. And we're only dealing with the real number line for these functions. The domain is starting with the real numbers, and so we are going to exclude these imaginary numbers or complex numbers that we get. So we only have two critical numbers of negative 2 and positive 2. So our critical numbers are negative 2 and positive 2. And then we want to find the concavity. And so we're going to take those critical numbers and we put them on the number line in order from smallest to largest. This breaks up the number line into these different sections, these different intervals going from negative infinity to negative 2, negative 2 to 2, and 2 to infinity. The second derivative is going to tell us the concavity. So I'm going to choose test points in each one of these intervals. So I can choose negative 3, 0, and positive 3 as test points. And I'm going to substitute those test points into the second derivative. If this second derivative is positive, the function is concave up on that interval. If the second derivative is negative, the function is concave down on that interval. So let's make a chart with our test points of negative 2 and positive 2, and we're going to substitute those into the second derivative. Let's use our calculator. I'm going to type into the y equals menu the second derivative. Which is 144 times x squared minus 4 over x squared plus 12 to the third power. I'll go to my table. I'm in ask mode. Let me clear out these, delete them. And we're using the test points of negative 2 and positive 2. Oh, excuse me, I made a mistake there. My test points, I typed in my critical numbers instead of my test points. So let me correct that. My test points were negative 3, 0, and 3. And we're looking at the sign of the second derivative. So we want to decide whether we have positive or negative. So we have positive, negative, positive. So on our intervals, we have positive, negative, positive. Anytime we get positive, that's going to tell us concave up. We get a negative, that tells us the function is concave down. So now we've identified that the function is concave up from negative infinity to negative 2, union with 2 to infinity, and the function is concave down from negative 2 to 2. And then we want to look for points of inflection And points of inflection occur when there is a change in concavity. So we can see that right here we have a change in concavity from positive to negative, so that means that critical number is a point of inflection. So we're going to have a point of inflection at the ordered pair -2, and I don't know the y coordinate right now. We have another change in concavity right here from negative to positive, and so we're going to have another point of inflection at the ordered pair 2, and once again we need to find that y coordinate. The point of inflection is something that is on the original function, so we're going to take these critical numbers of 2 and -2 and substitute them into the function to get that y coordinate. So we're taking those critical numbers of -2 and +2, and we're substituting it into the function f. That's 24 over -2 squared plus 12. 24 over 4 plus 12. 24 over 16, and that will reduce. 8 goes into both of those. 8 goes into 24 3 times, and 8 goes into 16 2 times. And we're going to get the same calculation for the other one, 24 over 2 squared plus 12, and that works out to be 3/2 as well. So we have our points of inflection being -2 and 3/2, +2 and 3/2. Thank you for checking out my videos. Have a great day.